Welcome. I'm a bit surprised with how many of you are there. I expected at least half that at this hour. So, okay, not to waste more time. The agenda. I will start with a description of Singleton and its problems in the area of mocking and in general testing. Then I'm going to propose a different approach to Singleton, which doesn't lose main benefits of Singleton as a design pattern while it solves the aforementioned issues. Then I will explain how this can be applied to mocking external APIs. And I will show a few more techniques. Mostly those are going to be dark alleys of C++, so if not necessary, don't use them. But, well, it's good to know that there are. Okay, so with the Singleton, there are few classic approaches in implementing the Singleton. First one is to keep the static instance in the class. So we can see the static object defined in the class. It's defined in source file usually then. The other approach is to have a pointer which is initialized in the get function. Obviously, this is not very thread safe or whatever because it wouldn't fit on the slide, but you get the idea. And the third classic approach is to keep a static variable within the function. All those three approaches, classic approaches, they share common problems. Mostly, the most important problem from our point of view from this lecture is that the instance creation, construction, whatever, how we made it, is bound to the same source file as the rest of the code, which makes it very hard in testing because it's very difficult to use test doubles. Well, I will mostly refer here in this presentation to mocks, as the title says, but this applies to other test doubles as well. The same approach can be taken with fakes or stubs. So if we keep the instance creation construction in the same source file as the rest of the Singleton code, it burns our hands when it comes to unit tests or any other form of tests, because the test cannot easily then supply a different instance because, well, the one is already created in the source file. So either we drop entirely the Singleton, we do not test it because we have no way to make a different instance, or we have to produce various, more than one binary for tests, so that the test of the Singleton itself will be a different binary and will use some not so nice tricks I will mention later on. And reminder sources don't use real Singleton, but instead use a stub implementation that stubs everything, including the instance creation. So if nothing else, if you would not take nothing else from this presentation, then at least please put the construction code to a separate CPP. This alone solves many of the issues. So, like we had in the previous slides, maybe this would be the best done with the first approach. The definition of the object should be put in a different CPP. I'll call it Singleton instance, for example. This separates a reminder of the Singleton code from the instance creation. So you can have the entire code tested and, well, you can use it in tests just as in production code, while you can substitute a different source file for creating the instance itself. Yeah, production build will use the file we have defined, and testing build will use either that CPP which constructs the normal instance or a different one that makes a test double. However, there are still problems with this. While it's much better than keeping everything in one source file, it's still problematic because we still have a single point of creation of the Singleton instance, which means that even if we somehow manage to use test double in tests, some kind of mock, that will still be a single mock for all the tests. Or again, we will have to split the output of the test files so that they will we will build few more binaries so that each binary could use different implementation of the Singleton test double. Which in general it leads to harder to maintain code. Yeah, so there is place only for one object, and another problem is that it's also because there is place only for one object. It's difficult to use some tests with the test double and others with real implementation. Like if you would like to use some kind of higher level test, module test, for example, then it's quite possible that you would like to use the real Singleton object that does its real job instead of using any test double. Hard to do that with if you are strongly bound to only having one instance in the entire application. Yeah, so if you need more than one test double, because if you test direct users of the Singleton, you will usually want to have a mock or stub to control the Singleton behavior while checking your class. While if you are doing the higher level test, then you probably want a real object or a stub that behaves much like a real object. It's difficult with a single instance. Building more than one target binary could be the answer, but building many binaries has its own issues. You have to take care in the build system not to build the same sources more than once. I have seen projects which went that way, that almost every unit test of every class was a separate binary file, and they kept building infinitely long because the build system was screwed up and built the same sources for dependencies for every of the unit tests separately, because, well, it's much more difficult to maintain it otherwise if you have different targets and they might have different options, and they sometimes did have different options. So you often are even actually forced to rebuild them time over time, which doesn't go well with short cycles of implementation and tests. But there are other ways. And this is the passive Singleton. I made up this name myself. I didn't find it anywhere in the internet, but maybe it's not a fresh idea, although I didn't find it so far. So the idea of passive Singleton is that the Singleton no longer takes responsibility of instance creation. It's someone else's job to create the instance. As you can see, the instance variable here is now just an ordinary pointer. It should be it should be ordinary pointer instead of smart pointer, because having a smart pointer would again take responsibility of destruction. We don't want that. This pointer is only serves single purpose, so that the get function can return the only existing instance. Now, the constructor sets this pointer to itself, while the destructor clears it. This way, we can easily assert in the get function, or, well, we could throw or use whatever else practice you might find feasible. Anyway, if it will be null pointer, even if we did no checking at all. It will immediately crash on the reference of a null pointer at the place where you call the get function, so you will get the full stack trace. It's much easier to find the real problem, where the function was called, expected an object while it doesn't exist. Now, you can wonder whether this approach is safe. There are since the get function or nothing else in a matter of the passive Singleton takes responsibility of creation of the Singleton object, then, well, it is indeed possible that we will end up calling the get function while no instance exists, and it will crash. However, the Singleton objects are not objects that you end up creating every now and then. You set them up at the application start, or in other service start, or whatever, such well-known points of execution, and then you never touch them again. So why not just instantiate all the singletons you want as local variables in main, for example, or whatever you see application or what you have there. And they are already set up. They will set up their own pointers. So every get will function will return the pointer, the singleton as expected, while the singleton object exists already. The additional advantage of this approach is that we are in full control of the order of creation. If it's the get function which creates the singleton, we can never be sure when the singleton actually is created. It varies depending on how the code actually, it might be, today it's created in some point and tomorrow the code changes slightly, someone called some new function somewhere else, and now out of a sudden the order of construction of singletons changes. So that's problematic, and that's even the easier case because at least it's explicit to the get function, so you know when it is. With the two first approaches where you just had a static variable in the either in the class or in the get function, then it's the order of linker dependent order decides when the object will be created and destroyed. So it's good luck with finding a bug when the singleton got destroyed while you tried to use it in some later singleton. It's really awful to find such errors. So while in this particular, with this approach, we are in full control and in full awareness of what the order is, because at the main or whatever else we choose, we are constructing the singletons in the order we need. We know that they will be destroyed in the opposite order, and everything is fine. If there is a bug, we immediately see where it needs to be solved, including a possibility of circular dependency in the singletons themselves. And with this approach, it's much easier to have a different test doubles in tests. In particular, you can have a mock, for example, instantiated at the beginning of test case, and just as if you would do in main, and the rest of the test runs just as in a normal code would do. It will call the get on the singleton, and it will get the object, which is our mock, as expected. The additional benefit here, besides that we can, in every test case, or even every block of a test, we could use a different type of singleton, is that also there is no persistent global state between tests. Since there is no global mock, it's just a local variable, nothing persists. There is no risk that tests pass or fail only because they are run in a specific order, and that would change if you would run them in different order because the state of the singleton changes between the calls. So this simplifies a lot. Also, it's much easier to actually validate state of the singleton, whether this will be expected calls on the mock or whatever we do with the stub. We do this at the end of the block, either explicitly or in the destructor of the mock or stub. There is no need for explicit call to any kind of verify or alike functions, or no need to clear anything because it's done by the destructor. While, let me remind you that this is we sacrifice, the only global thing we have is a pointer to the singleton object. So it's good to know that since it's a C pointer, it's initialized to null at the binary level. There is no risk that we will start an execution with the pointer being uninitialized. It's nulled before anything else. So we can be sure of its state when we start, regardless of any orders of construction or whatever else. This will always be okay. Though the disadvantage is that now you have to use this singleton in a polymorphic manner. To be able to provide singleton mock, well, you have to usually be able to override virtual functions and to do them whatever your framework needs to. This could be possibly avoided by using, well, let's say link time polymorphism, but that's not a nice way. And well, usually it's easy to do the polymorphism anyway. So the passive singleton, as I described here, offers means to get the single object just as the normal singleton does, right? There is a get function which returns a reference, so there is no doubt of the ownership, as we heard on the previous presentation. It acts as an ordinary singleton. However, it doesn't construct the instance. Someone else must do it. If any of you watched the Clean Code episodes by Uncle Bob, you will recognize that Uncle Bob introduced a boundary in the source code, that there are some parts of the code that are well, generic, let's say so, and there are parts of the setup parts which are not so generic, because, well, they have to construct concrete objects. They cannot operate on interfaces, or at least not enough. This applies cleanly to the passive singleton. The main is there, the part which constructs concrete singleton implementations, while the rest of the code uses an interface and doesn't care what's the interface, how it is implemented. And it pays off in the tests, where we can then supplement a mock or a stub. Now, with the, or maybe let's return it to it back later. Yeah, what I already talked about. Each test suite or even individual test case can start from constructing the instance, possibly a test double, runs as even a singleton with any normal singleton, and the destruction which with normal variables, I mean local variable or a smart pointer, will be done automatically by the compiler anyway. Everything clears nicely. We check every expectations we made up, and every global state is cleared back to the original state. Bonus features include, well, aforementioned no persistent global state between test cases. Trivial global variable, that's also what I already mentioned. The pointer is a trivial variable. It's initialized very early. There is no risk of order dependencies. We can be sure that it's in a good state. And explicit construction destruction order. Well, if some of you read the modern C++ book by Alexandrescu, there if I recall correctly, he starts with a singleton pattern, which he does on policies, and there are various fancy policies, including Phoenix policy, which recreates the singleton whenever it dies and it happens to be needed again. Well, while this looks great in the book, I think that it's rarely really useful, because if you need to recreate a singleton that was already destroyed, I would rather consider it a flaw in the design of the application or its implementation, rather than a feature. Right? It's workaround on problems you have otherwise in the code. You shouldn't just rely on such behaviors, because it will end up to problems in the runtime that are very difficult to catch. Singletons which are constructed, for example, before main runs, are not so easy to catch with any no infrastructure for catching or logging errors in main you might have be having will not work. You will not catch an exception, because it will just crash the application. The same goes with destruction of the variables, global variables. It's even worse with the variables that are static in the function, because they are even more dynamic. They are destroyed in the opposite order in which they were created, which is unsurprising. But unlike with the global variables, the order of creation depends on how your application calls those functions which declare those static functions. If you happen to get a different input and, for example, skip some functionality, the corresponding singleton will not be created and will be destroyed also in the different order. And good luck with testing this and finding out when the application happens to have a bad order on client specific configuration and never on your test configuration. That's why explicit construction and destruction is much, much better, in my opinion at least. Now, when it comes to external API, there is a lot of it. POD6, WinAPI. Sometimes you might even consider the C library itself worthy of mocking. Like you could trace, for I don't know, memory allocations, for example, or file operations. Typical approach, at least from my point of view, is to use link time polymorphism. In building tests, you do not supply the ordinary library you would be expected for the external library. Instead, you supply your own sources, which implement the same function, having the same signatures, but in your way. They are usually kind of stubs. This works fine, provided that you really have a good grip over the build system and you can control it very well. If not, you will end up in cases where you have both versions, the real version and the stub version in the build system, and depending on which goes first, the actual sources will be linked differently. You may even end up in situations like when some parts of your program, especially if you are using dynamic libraries, some parts use mock or stub, and other parts use real objects, and the results might be quite surprising. And then again, there is the problem on one size must fit all, because even if you do so, if you do it successfully, you still have a one stub. Like you have a one global function like bind or accept from PROS6, and you provide your own implementation, and then what? You have one implementation and many possible test cases. You might sometimes want to mock it so you verify it's called properly, and otherwise you might want to just stub it so that it will pretend to work without doing anything external. While with this approach you have just one function and one definition. And usually it's difficult to apply this approach to just one function because to do it properly, you should not include the actual library, only your stub library, which means that you have to stub every function that library provides. Otherwise, you will have unresolved references. If you don't want to do that, you stub only your one function and attach also the real library. But then again, you are at the order problem, because depending on the order of the files provided to linker, you might end up not using your stub at all, only using the real implementation. So it's difficult to play and maintain. And notice also that this depends on the build system. Now you no longer work only at the source code level, but you have to take care of the build system. I myself prefer to abstract away of the build system. I would like my code to work just the same with any sane build system. While we using the link time polymorphism, you often have to take much care of the build system and on the platform you are in, because various tools have various behavior. It's not those things are not defined well. They are defined per tool rather than per standard. So it adds additional complexity. Now, this problem of the external API could be solved with classic object-oriented approach, right? Instead of using global functions, you introduce an interface which covers those functions. Like you could, for example, have a socket interface which has a accept function, bind function. They will probably, for the simplicity, have exactly the same signatures as their corresponding global versions. And then you implement this interface either using real functions. Don't forget to prefix the call to real function with double colons, because otherwise you will end up making recursive call if the signatures are identical, or you can provide any implement any mock or stub or whatever else you need. Now the only problem is that you cannot use the global functions directly. Instead, you have to use the interface. There are two approaches for this. You can either make it clear dependency injection. So every class that uses sockets will take as an argument to the constructor the sockets interface, and this way, well, you can control everything. Every class can be easily tested by providing test double, or can be used in a real way by providing a real object. This is fine to some degree with most interfaces, but it doesn't work very well with interfaces that are used really a lot, like logger interface, for example. You would end up dependency injecting logger into each and every class. In the very end, when it's really bad, you have to add the logger interface even to simple array classes, which might possibly try to log something or some error conditions. And you wouldn't expect those to take anything else than the resource they manage, while they have to now take the logger interface. So this doesn't work very well on all levels. There is a level at which you usually would say that, no, I'm not taking this as a direct dependency. But we will get back to it. This approach with the object-oriented programming allows coexistence of multiple test doubles and even a real implementation at the same time. This is the main benefit of the interface in object-oriented programming. Well, it defines what it can do, but not how it does. So you can at the runtime provide different implementations. It's easy to apply this approach to only some functions. Like you don't want to start with mocking entire POSIX. You might be just fine with those few socket functions, at least at the beginning, right? It's especially important. This is especially important if you are introducing this approach to already existing code base. It's difficult or even not possible often to rework entire code and change it everywhere. So you start with just few functions and then add on when the opportunity arises. So the solution must allow that, and this one allows it. You can even start with a single function at the beginning. There is this problem of dependency injection versus Singleton, because the other approach to dependency injection is to use Singleton. Instead of directly taking the interface in constructor, you just assume that there exists a single implementation of the interface, and you get it from the Singleton pattern. And if you go this way, and I would go this way with interfaces like Logger, for example, then why not passive Singleton? Because if you go with the ordinary Singleton implementation, you end up in the same problems that the Singleton has at the build, in building unit tests and other forms of tests. That it's difficult to provide different implementations of the Singleton. So if you choose the passive Singleton approach, then you connected both solutions, and it's now easy to mock, stub, or use real implementation of external interface while having a clear Singleton without the need of direct dependency injection. The disadvantage of this approach is that it often leads to inconvenient naming, because it's pretty nice to see and accept, bind, or connect functions in the code. If you know the domain, you know exactly what those functions do. You know how to find them by grep and so on. While if you introduce your own interface, now you have many choices how to proceed with naming. For the starters, you will never have a direct call to the global function. So you will always have some prefix, whether it will be a Singleton or it will be a dependency injected interface, whatever, you will always have a prefix of the object on which you call the function. Then if you use the same name of the function as the original function, then it's at least easily to be found by grep. But it looks nice with the provided example of sockets where the functions are pretty short, like accept and bind. But it often happens that in larger projects, C-like APIs have really long names, encoding project name, module, and various other stuff, so that to ensure that the name will never clash, and it's pretty obvious where the name comes from. And if you use this, then the call with the singleton or dependency injected object becomes really long and inconvenient, because it basically repeats the same information. You have that your module something something calls function something something do something something, and it looks awfully. It not mentioned that it makes lines very long. So that's a disadvantage. However, disadvantage can be worked around with a mixed solution. You keep normal calls in the production code, just as you did always, and you use link time polymorphism to provide stubs in tests, just as you would do in the original solution. Now, the idea is that the stub implementation you provide forwards anything to a passive singleton. So you connected both solutions. If you do this this way, the stub has no real logic. It just forwards to an object it assumes that exists because it's a passive singleton. While the tests, you write the test as if you would write with the passive singleton. So you, at the beginning of the test or in your test suite or whatever else suits you, you construct the singleton object instance to be whatever you need, whether it will be a mock or any test double or the real implementation, and the stub will forward properly to your interface, which will do what is expected. However, the disadvantage of so you can have many test doubles this way, even though you use the link polymorphism, which I previously described as one size fits all. Least impact of production code. The production code doesn't change at all. The production code still calls global functions as it always did, which might be an extra advantage if you have hard times convincing your colleagues to the new approach, if they are not particularly fond of those dependency injections and prefixes that they now have to use for well-known global functions. So from their point of view, the production code never changed. It actually never changed at all, because it really calls only those global functions. The link time polymorphism assures that the production code, there is no forwarding or whatever else in the production code. It's only done in the testing code. Yeah, no virtual call in production code. I expect that in most cases, doing virtual calls nowadays shouldn't be a cost that you are afraid of, or you should be afraid of. Although there are those cases of embedded software, or if you call this function really, really often, just in case, this approach solves the problem, because in the production version there is no virtual call. You call the global functions as you would do without testing at all. However, the disadvantage of this approach is that, again, it's hard to use real implementation in tests. So it's much harder to, for example, do module tests, because you already stubbed the actual library while building the tests to allow the link time polymorphism. You have no direct access to it. You can work around it with dynamic libraries, for example, but it gets complicated and it's no longer really platform independent, because when you go to dynamic libraries, they have their own issues depending on the platform. So it's not so nice anymore. I don't know how to avoid that, sadly. And no way to apply this approach to some functions, which again is a problem which might be a blocker. Because again, that's the property of link time polymorphism. Either you stop all functions, or you end up in playing with the linker or whoever will get first, which is not a nice game to play. So better not do it. But if you don't do it, then you have to stop all functions immediately, which again is a good point to make your APIs modular, because if you do them modular, it will be easier for someone else to stop just a few functions instead of a huge library. Now, there are some other techniques. As I mentioned in the beginning of in the agenda part, in my opinion, those are dark corners of the language, and they often don't even rely on the language as per se, but they rely on the tools, the compilers, the linkers, how the system works and loads your application. So they are not nice. They are not really easy to move across different platforms. But if need be, if you are so desperate, it's good to know that at least there are some tricks there. So at link time, there is such a option wrap in LD, but it's for Linux only, that allows it. If you provide a function name for C++, it has to be the mangled name, which makes additional disadvantage. You provide the function name with this parameter, and if the linker gets it, instead it expects that the code will use wrapper name and real name, and will resolve the name to the wrapper name, while the real name it will resolve to the real function. This way you can easily wrap a function in a portable way, because the linker is aware of what you are trying to do. So it's much easier to shoot yourself in the leg with this option. It's easy to wrap a function so that your own function is called, and then in your own function you have the possibility to call the real function by using the other name. It's double underscores real underscore and the name, mangled name if it's C++. This way you can easily stop each individual function. That's again advantage, because you can do this for individual function. It's advantage if you do it for few functions. It's a disadvantage if you do it for the entire library, and then you have so long wrap options, so many. So you can do this individually for every function. You could use this you could connect this approach with the Singleton, so that your wrapper would instead call to the Singleton, and the Singleton would either be a mock already or would call to the real function. This solves this wrap option solves the problem of not being able to call the real function once you go with the link polymorphism approach. Next is violate the one definition rule. As you can imagine, if you violate a rule, you already in not so good place. But well, you can do that. You can override functions by injecting to the linker your own definition before the actual definition, and then the linker will use your own definition. It's playing on an undefined behavior, and it can end bad. But in most cases, it should just work. It's not a nice solution. It's horrible to maintain or to move to a different build system, and especially advanced build systems where you do not specify by hand every particular library, and the build system might just order them as it wishes, and then you have no means to control this. But well, it should work, especially if you rely only on a static definition in a single CPP, where because this approach is difficult to override by the order of linker, because you have at the very bottom your own definition of the function, and since it's static, it will not affect other CPPs, but you then end up duplicating the same stub function over and over again. So that's, well, I said it's a dark corner, right? Other techniques are dynamic linking polymorphism. Here are a few more tricks to do. Well, I'm focusing here on Linux because it's what I end up using recently mostly, and I think maybe this is what most audience uses. But there are similar solutions to the on Windows platform. Then again, this again shows that how much dependent they are on the platform. You probably could do most of those things on Windows as well, but this is done with completely different API. Often just the idea is the same, but the technical details are much different. And so you have to basically redo your work if you want to be platform independent. Oh, so the dial sim with RTL LD next. This parameter is specified by POSIX, but it's not defined by POSIX. In practice, it works this way that the dynamic linker starts to look for the symbol starting from from the next position of where you are. So this way, you could substitute your own definition of a function over what, for example, libc provides. While you could still use this approach with the RTLD next to find the original function. Like your library provides the definition, for example, for malloc, while you use this DLSim to find the real malloc starting from the next library, and you can use either your own definition or the real, or well, just wrap it as you please. Another approach is to use LD library path. You could inject entire fake library by introducing this library to a directory that will be checked before the other directories are checked for the libraries. It's somewhat difficult because you have to write your entire library, but I'm not entirely sure. Maybe if you write a library that covers only few functions, the linker will just keep looking in other directories, so I guess it will work. For testing, it's fine. Otherwise, I wouldn't use this approach. Definitely, you can cheat around system libraries this way, so it's somewhat easier. And a similar approach is with LD preload. The idea is more or the same. However, this forces loading of a specified, but there's a semicolon separated list of libraries to load before loading everything else. So this way you can ensure that your wrappers or your mocks will be loaded first and will be found first before the real implementations. And as I said, those are strongly environment-dependent solutions. I wouldn't be surprised in problems even if moving to a different version of a similar system. They also depend often on the build system you have. So this is a lot of trouble. That's all. In addition, it's outside of the source code. So this again creates a problem of competence, because if you hire developers, you rarely can count that they will be able to deal with the nasty details of build system you might be using just now. And so they will have to rely on someone else to solve the problems of unit testing. However, what's worth mentioning is that using those approaches might help you with getting the real implementation of functions that you otherwise stopped with the link time polymorphism, because you will just obviously provided that they will be provided in a dynamic library, because if they were provided only in a static library, then nothing helps you here. There is other trick, source level hackery. And there are libraries mocking libraries that use it. You can find the link in the reference, and here is the lecture about it. There is an option include in GCC. I'm not sure whether Visual Studio provides a similar option, but I wouldn't be surprised if it did. That allows you to force include of a specific header before anything else for every CPP file that you compile with this option. This way, you can rename with the preprocessor functions. Like you have a send function that you want to mock. So you do the define send as, I don't know, utsend. And now every library function, the library function send is named utsend, not send, because the preprocessor takes over. Provided, obviously, that the function is introduced as a function rather than with preprocessor, which is not always the case. If it's introduced with preprocessor, you might end up with other problems again. And while at the same time you introduce a new variable like sd function or anything else with the same name that's expected with the send, and now everyone who uses send uses your variable, while you can still use the original function because you renamed it to utsend. So this is doable. Another, and that's really it's hardcore in my opinion, but it's doable, I guess, because there are people with libraries who do this, is to do binary level hacking. If you know how the object layout is in C++, then you can just play with the binary. You can create, for example, the library I'm mentioning here offers at least two approaches. First, you can create a mock object without the typical trouble of libraries like Google Test, where you have to inherit the interface, mock every function, keep them in sync with the original function, which is particularly painful because Google mock still doesn't use override, so it will not even tell you that the arguments changed. This library goes in the way of the managed languages, where which have a reflection much better. Well, they actually have reflection, unlike C++. So it tries to do the reflection by playing around with where the virtual table pointer is located at the object address and what it points to. So it just returns an object that happens to have a pointer to a synthesized virtual table that points to mock functions. This works nicely in the sense that you can easily create new mocks and but well, it's you are relying on undefined behavior entirely. It will work typically because those things are stable usually, but well, it's risky. And another approach they are doing is to mock a function by overriding its initial instructions by a jump to your own function, which again is hardcore, I would say. But you can do this. And another last thing, just briefly mention, there is a problem of testing main. Namely, main is a special function. You cannot overload it, or there is little things you can do with main. And in particular, you cannot introduce your own main. You cannot have two mains and call one from the other. So if you would like to test main, it might happen. For example, you might want to test output parameters, command line parameters, return value. For simple command line tools, such tests could very well test entire program. To avoid the problem of main, make a trivial implementation of main that forwards everything to a test table main, while test table main is now an ordinary function. So in your unit tests, you can have any main your framework requires, while there is a test table main function that you can just simply call like any other function. If you want to test it really deep, you can provide not only the command line arguments, but also output and input streams to cover everything. Then you can, for example, the test table main would take two input streams and two output streams and one input stream. And in your test, you would probably provide a string stream, so you can control whatever you push into the program and validate whatever you got back. This, however, keep in mind that this forces you to use a single approach. So if you would use it this way, then if your program uses different means to output than streams, you might end up having problems because you will not capture this, or you might not capture this. But it's possible to do it like this. So now the references, I particularly recommend the three first lectures on mocking. The first covers the binary hacking library, but it also has some generic. It covers in general the testing approach, what to test, what not to test, how to test. The second is it's just a lightning talk, so you can watch it in 5 minutes. The third is again it describes a different approach in mocking framework. Some of the tricks rely on those which I described here, rely on the ideas from this framework, but it's also a generic about testing. So it's nice to watch them. I recommend. And well, because people often say that my slides are dry, here you have an image. The idea was not mine, it was one of those lectures. And any questions?
Yeah, we have time for 1 or 2 questions. Anyone?
Well, I guess no questions then.
No? Okay, so
Bartłomiej Migaj speaking from Delphi audio team. I have a question. You have presented some better or less known methods, and what of them is the most common used and works best according to your experience?
Well, what's most commonly used highly depends on where you work. At the projects I worked, most commonly is used this plain old link time polymorphism with lots of violation of the one definition rule. So legacy, to be clear. But and I'm not particularly proud of that. Well, at least I didn't do it, so I'm just working there. I think that the best approach here would to be use the passive singleton, because I think it offers not only benefits in the testing area, but it just makes the application slightly better. There is one more benefit that I didn't mention because it doesn't relate to testing directly. This is again the choice between dependency injection and singleton approach. Dependency injection is fine if you do enterprise. If you can afford having lots and lots of pointers. But if you are not doing enterprise, or if you are doing for really tight systems that you cannot afford to have lots of memory bound to pointers that point to one the same value, there is really nothing wrong in using singleton. It's just that you have to use it properly. The classic approach often leads to problems, and I don't consider it a proper use. I think that my proposition with the passive singleton is far better. A good indication is that if you if you switch from a 32-bit platform to 64-bit platform, and with that your program doubles in size of used memory, it often indicates that you just use lots of pointers. And if you happen to use lots of pointers to the same few objects, then well, yeah, if you are on a PC, then that's usually fine, no cost. But if you are not on a PC, then it might be a trouble. So using a singleton might not be so bad in those cases.
anyone else? Okay. I think that's time for official announcement. And Adam, many thanks for this great presentation. And you don't know that Adam is a speaker during Code Dive and one of organizers of Code Dive 2. And Adam unfortunately missed official acknowledgement at stage 1. So you should make a big noise and big applause for Adam now.